All right, what are colligative properties? Colligative properties are properties whose value is going to depend on the number of solute particles, not necessarily what they are, but depend on how many there are, okay? So the value of the property is going to be dependent on the concentration of the solution. More concentration, more particles of solute, right? The higher the concentration, the more amount of solute you have, and therefore a greater effect on these colligative properties. The difference in the value of the property between the solution and the pure substance is what we are going to be focusing on. What was the pure solvent looking like? And now that we've added a solute and made a solution, what's the new property of the actual solution look like? And compare those two, all right? And it's all, again, based off of the intermolecular forces. What intermolecular forces did we bring about? And what does that mean for the interactions between the solute and the solvent? Vapor pressure of solutions is what we're going to talk about first. The vapor pressure of a solvent is above the solution, right? That is looking at again, the amount of gas particles above the liquid, okay? Technically, when we make a solution, when we make a mixture occur, vapor pressure lowers. That's the phenomena, vapor pressure lowering. Why? It's because the solute particles have actually replaced some of the solvent molecules at the surface, okay? And we're going to establish whether that solute is a non-volatile solute. That's the one that we're going to deal with. So by replacing some of the positions at the surface, the solute particles have effectively pushed the solvent back down, okay? In addition, that idea that the solute is holding on to the solvent with intermolecular forces and not letting it escape, okay? So vapor pressure effectively lowers. The concentration of a solution will draw the solvent molecules towards it because of the natural drive for mixing as well. So it's not only intermolecular forces, but it's also entropically favorable for the solvent to stay in the liquid form than it is to go out into the vapor. Now, let's go ahead and look at the calculation. We're going to talk qualitatively always first, and then quantitatively. What can we do in order to calculate that change in pressure? The vapor pressure of a solvent in a solution is always going to be lower. There's the qualitative, right? Lower than the pure solvent. So by adding in a solute, we will effectively keep the solvent in the liquid form and change the vapor pressure. The vapor pressure of the solution is directly proportional to the amount of solvent in a solution. We will be using mole ratio here. The difference between the vapor pressure and the pure solvent, this change in pressure, right, state function, is the mole ratio of the solvent or solute, multiplied by the vapor pressure of the pure solvent. So this is the pure solvent vapor pressure multiplied by the moles of solute divided by total moles. Beautiful. And that would equal the change in pressure. Another form of this is Raoult's law for vapor pressure, where you can actually calculate the new pressure of the solution, right? The pressure of the solvent in the solution by changing one little thing, by changing the mole fraction here. That mole ratio or mole fraction, if you use that of the solvent, moles of the solvent divided by total moles, and you multiply it by the original pure vapor pressure of the solvent, then you would get not the change, you would get the actual new pressure of the solution. All right, so just to describe a few more things, it's very important to make sure you use the right mole fraction that you want to use, okay? Because the mole fraction is always less than 1, the vapor pressure of the solvent in the solution will always be less than the vapor pressure of the pure. We will not be doing Raoult's law for a volatile solute, okay? There does come with it a idea of Dalton's law of partial pressures, right? So you can see what it looks like, but I will not be giving you the question for Raoult's law of a volatile solute. So this would be things like a liquid-liquid interaction. So things like ethanol in water or acetone in water. Both of those are liquids. They would be miscible, and the vapor pressures for both of the solutions from the pure to the solution would drop, but we're not going to do this type of setup. So skip this one, okay? Because vapor pressure lowering occurs, there are other effects that occur as well. So in a solution, vapor pressure lowering occurs at all temperatures. So this results in the temperature required to boil the solution being higher than the actual boiling point of the pure solvent, right? So if you think about water, all right, let's go back to making spaghetti, because I'm always about food here, if you haven't noticed. Gotta love spaghetti. You want to boil pasta, right? You want to boil some water to make the pasta, to cook your pasta. So you put a big pot on the stove, you put it in water, you throw in salt, not only to make it taste better. Why else do you throw in salt? What does that do? It does not boil faster. That's a common misconception. It does not boil faster. It actually creates a homogeneous solution. You throw salt in water, you have now created a solution, which causes the vapor pressure of the water to lower, right? Which means that more energy is required to get the water to boil. Well, what does that mean then for us? Why the heck would we do this? Because you've actually increased the boiling point of the water. You cook your pasta faster. All right. It doesn't boil the water faster. It boils the water at a higher temperature. And so that makes the water boil hotter and your pasta then cook faster. Cool, huh? Another favorite dish of mine is ice cream. If you have ever made ice cream at home from an old-fashioned ice cream maker, you need rock salt. You take ice cubes, you throw rock salt on the top. Why? I don't know, because people were crazy back in the day? No, it's because they were geniuses. It causes the resulting temperature required to freeze the solution to be lower than that of freezing at the pure solvent. So we start to melt our ice, but at a very cold temperature. And that ice liquid then surrounds the inner container of your ice cream base, your curd and custard, if you will. And then as you start to stir, because old fandangled mechanical crank, right? None of these electric, we're going to use electricity to cool things. No, we throw rock salt on ice that creates the water temperature of the ice to be colder and a liquid still, right? You start to melt the ice, make it a liquid, but it's super cold. And then you can freeze the ice cream custard faster. Dang, super cool. I live in Orange County, so I've never really lived in snow, but I do know that's also why we throw ice on the road, not only to increase traction for wheels, but also to melt snow on the road. It's still at that cold temperature, but if you throw ice on the road, if you throw salt on the road, then it will start to interact with the solid water and it will lower the freezing point. So two things that we're going to talk about: boiling point elevation and freezing point depression. What actually happens chemically is that the interaction between the solute and solvent drives the triple point backwards, drives the triple point down, and it expands the liquid phase for the solution rather than just the liquid phase of the pure solvent. Notice this, right? It is expanding out this phase diagram liquid form to create more of an opportunity for the intermolecular forces. What? Intermolecular forces are cool. So the freezing point of the solution is lower than the freezing point of the pure solvent. All right. The boiling point as well is going to be elevated. Let's talk about the freezing point first. The change in temperature of freezing, delta TF, is going to be equal to the molality times the KF. Now, this is a proportionality constant, KF. You can look it up on a table. It's in degrees Celsius per molal, okay? So it is going to be molality here. And I'm just going to change one little thing about this, this freezing point. When we talk about having different types of solute, the overall equation that we are going to use is incorporating this little I. This I is called the Van't Hoff factor. Now, I here, if we have a molecule, right, such as sucrose or glucose, if we're throwing a molecule in water, I is equal to 1. If we're throwing an ionic compound in water, we're dissociating that ionic compound. We don't have NaCl, we have Na+1 and Cl -1. So the I would be 2. All right, we're going to talk about the number of particles that will be dissociated or will be in the solution, okay? And that will aid in our calculation. Right now, we're just gonna take this factor right here, this delta TF equals I times molality times the KF. And we'll be able to see that the KF is going to be a variety of different things based off of whatever solution we have or whatever solvent, okay? It's solvent dependent. Here is table 13.6. You can see the normal freezing points and normal boiling points. Again, those are at 1 atm, and the KFs and the KBs according to that chart. Now the KB is going to be used for boiling point elevation, and the calculation will be looking very, very similar. These KFs and KBs you do not need to memorize. They would be given to you if you needed them. Boiling point elevation, same idea. Non-volatile solute, we're going to just stick with non-volatile solutes for all of these things. Delta TB, change in boiling point, is equal to molality times the KB, all right? Now, we are going to have delta TB is equal to I times the molality times the KB as well. And we'll talk about the Van't Hoff factor in just a little bit. Osmosis is another colligative property, slightly different than boiling point elevation or freezing point depression or even vapor pressure. Osmosis is the flow of a solvent from a solution of low concentration to that of high concentration. The solutions are separated by a semi-permeable membrane. We can think about our own bodies here, right? We have osmosis. When we drink a lot of water, our body can actually absorb the water because things like our blood is a solution, right? There's a lot of different particles going on through that. And all of our cell walls are semi-permeable membranes that allow some things to flow through, but not all things, okay? The amount of pressure needed to keep the osmotic flow taking place is called osmotic pressure. And the osmotic pressure is abbreviated pi, and it's directly proportional to molarity of the solute particles. So we've seen our number one concentration units, mole fraction, molality, and now we're at molarity again. We do have the osmotic pressure of pi equal to molarity times R, which is our gas constant for pressure, for integrating pressure, times temperature, okay? Let's talk about the Van 't Hoff factor. The Van 't Hoff factor is important for ionic compounds. If you have a molecule, and remember, molecules do not dissociate or ionize in water. Ionic compounds dissociate in water to produce multiple solute particles for each formula unit. NaCl as a solid is one unit. When it becomes NaCl aqueous, it's actually Na plus one and Cl minus one. So where we had one particle before, we now have two particles at the end of the day in the solution. And so it's really that Van 't Hoff factor I that will be used to make sure that we contribute the number of ions in the solute. All right, so if you have, again, a molecule, your I is 1 because there are no ions formed. If you have NaCl, you make Na plus 1 and Cl minus 1, that would be 2. Okay, if you had something like MgCl2, that forms a magnesium cation and 2 chlorine anions. Van 't Hoff factor is 3. That's how we would estimate the Van 't Hoff factor. The higher the Van 't Hoff factor, the more effect of the colligative properties. So the measure of the Van 't Hoff factor can cause the delta T to be lower than that if it was a molecule or other non-dissociating compound. Typically, what we do for I expected is just look at the actual ion count. They are kind of different than what is measured in real life, and that's because in real life, not all of the components of those ionic compounds will dissociate. But notice how we have a non-electrolyte, these are molecules, have an Van 't Hoff factor of 1, and then all of the other ionic compounds will have Van 't Hoff factors counting up the number of ions they produce. Why are colligative properties important? Well, we can think about our blood, right? When we think about normal red blood cells, the isomotic solution, it's looking at the osmotic pressure, right? And the solution has the same osmotic pressure as the solution inside the cell, right? And so there's no net flow of water in or out the cell. When we see shriveled red blood cells, like the picture in the middle, it's because there is higher osmotic pressure in the solution than outside the cell than inside the cell, okay? So as a result, there is a net flow of water out of the cell, causing it to shrivel. And then the hyposmotic solution is when water would be driving into the cell and causing some of these cells to swell up and to look like bloated donuts instead of just normal everyday donuts.